There we go. Okay, should be recording. So let me hand the floor over to. Wow, is it Pico pipetter or is that 10 to the minus 12 part of the Pico 10 to the minus 12 pipetter?
That's just like the logo, if you will.
I got you. Okay, well let me hand it over to you guys, and you can share with us your pipetter design.
All right, sounds great. Thanks. Sorry for the delay, everybody. We'll try to get to this. Hopefully, stay somewhat on time. At least give you guys some of a break after all these Zoom meetings today. But welcome to our presentation of the Pico pipetter, our automatic pipetter design. If you go to the next slide, we can go over our team. So the team is comprised of myself, Ryan, Jose, and Andrew, who are joining me. And we were tasked with designing an automatic pipetter for the UF Biofoundry's autonomous microbioreactor project. So just because we're the first pipetter, I wanted to preface that the volume needs of the customer are being addressed with 3 different volume capacities, with our design targeting the 100 to 1,000 microliter range. And you can see the picture to the side, that's our final prototype design. So if you go to the next slide, we can go some of the high-level view of the design. So you can see the overall dimensions of the pipetter are about 50 millimeters by 50 millimeters wide and then 200 millimeters long. For reference, this is about the size of a standard water bottle, so fairly compact for volume it delivers. That outside casing and the motor cover were 3D printed with snap fits, so we have easy removal, so you can look into the motor and the wiring and maintenance as required. Within there, the system uses a stepper motor to drive a lead screw, which actuates a piston cylinder. This is going to create a vacuum to retrieve fluid up through the pipette, or in the other way, expel the fluid using that lead screw traveling on the stepper motor attached to the plunger. Additionally, at the bottom of that lead screw travel, there's a tip ejector that when the drive nut reaches the bottom, it's going to push down and then push the actuator to shove off the pipette tip when it needs to be discarded. Additionally, at the top of the travel on the other side, as you can see there, there's a home limit switch. That's to zero our location within the travel of the lead screw. So we can make sure we're not going to be slamming it out of the bottom on accident or going up to the top, which would obviously damage the lead screw nut and other components. All right, you can go to the next slide.
All right, so now we'll go into some of the design or evolution that we had. We really wanted to focus on creating a simple and small design that was reliable, but was still able to complete all the requirements. And to do that, essentially, like we said, we wanted to focus on compactness. And essentially, we were able to shave off 15 millimeters off the width and thickness of our overall design, as well as still focus on maintenance and mitigating failure points. And you'll notice that in some of the iterations of the separate parts we had in our design. One of the biggest changes we had was combining that external case you see in the left, that's blue, and combining that with the shaft housing. And that overall just reduced the amount of parts we had, the size, as well as the reduced the amount of fasteners we had. So getting more into specific parts and how they've changed. We'll go ahead and look at the drive housing, or drive shaft housing here. One of the first things we did was increase the height of it, which helped with our volumetric capabilities of how much water we can actually take up into the pipette. We also started experimenting with some snap fits, as you see in that bottom left image. This was a snap fit for our bottom plate or our pipette attachment plate. Through some testing, we noticed that we started to get some weaknesses and failures from these snap fits. So eventually we decided to move on past that. And you'll also see that in the next slide. But as I mentioned before, we eventually ended up combining the external housing with our drive shaft housing, as you see there in the bottom right. To do that, we had to make some modifications where we could add like the gantry system to this actual housing, as well as openings, so we can create that internal limit switch and keep all that wiring internal. One last thing to actually note about that, we were having some issues initially with mounting our motor to the drive shaft housing, just due to the holes being really close to the edges of the sides of that housing. So we initially created this small slit that we can more easily put in those screws into the screw holes, as you see in that top right. But we still started to get we're still having some issues with that. So as you see in our final design in the bottom right, we were able to just thin out that shaft housing just a little bit, as well as make those slits a bit bigger, which then made it much easier to put in that motor mount. Lastly, about those slits, they also act as a insert for our snap fit of our external housing that houses the motor. All right, now looking at the ejector mechanism, as we said, here's the bottom plate or the pipette attachment plate. One of the first things we did was increase that hole diameter so we can then incorporate a heat set insert where we would essentially hold our plunger, or it would be the piston for the plunger. My apologies. We then, like we said, we experimented with the snap fits and we tried to use those and we started to get those failures and eventually we did away with those. Lastly, we increased the thickness of this plate as we learned a lot from our just testing from our ejector mechanism, and we felt like this is a point where we needed to add some strength to our design. So we went ahead and increased this thickness of that plate there. Next, we'll go ahead and look at the ejector sleeve that we have here. One of the first things we did was added that extra level to the ejector sleeve. Part of the reason we did that was because of that increase in height in the shaft housing, as well as it added support when the plunger was going, or the piston was going through the actual sleeve. And we also did a lot of altering in the printing direction and quality, just so we can get the best surface contact and surface quality of these parts, as that ejector sleeve would be sliding between that bottom plate, as you see with those two slits next to that hole opening there. And something we also did was we would develop a snap fit between that ejector sleeve. For instance, in that black and yellow part there, those are connected via snap fit. That way we can easily take those apart if we needed to disassemble. All right, next we're gonna go ahead and look at the drive nut and plunger. Had a couple changes here. One of the first things we did was change the connection point of our drive nut and plunger from the top of the drive nut to essentially the bottom. That allowed us to get more increased volume metric capabilities for our pipette. And we also added a counterbore to our drive plunger. As you see there in the bottom right, we're able to now have a flush finish between the lead screw and our drive nut. Due to that change you saw in that last iteration of the drive shaft, we had to reduce the width of this part as well. And to do that, we had to cut out a portion of the drive nut just to make it just easier to install onto the, we had to make it easier to install the lead nut screw onto the drive nut. Lastly, a small change we made to the plunger, just about the only change we made, was we went from aluminum to precision ground steel material. That way we can have better finish and better contact between the actual plunger and the piston. That way we wouldn't have or mitigate pressure losses between those two parts.
So for our design analysis, like Jose said, we wanted to keep our design simple, and that kept our analysis pretty simple, and so we can focus on what customer needs we met. So first of all, we had to hit a ±5 microliter range, and through our calculations, we were able to hit about 1 microliter per step, which is well within that range, and that's about what we got when we tested. And then as far as preventing any aerosols when we're dispensing, we got a flow rate of 322.5 microliters per second. And I was using the 100 RPM rotational velocity that the testing code already had in it that was provided to us. And using that, we got a Reynolds number of 474, which is well below 2300, which means we're well below turbulent flow, and then we're not creating aerosols. And then to make sure we could hold the fluid when we picked it up, we needed an O-ring leak analysis. So for this, our pressure between the O-ring and the plunger itself needs to be greater than the internal pressure. And so using a sample calc from a syringe example, we got the pressure inside of the pipette came out to be about 5 megapascals. And then estimating the pressure between the O-ring and the piston itself, we got 10.6 megapascals, which is about double, meaning we are sealing. And another thing to note on that 10.6 megapascals is it is an effort very close to the accepted rule of thumb that a rubber O-ring holds around 1500 PSI, which is about 10.3 megapascals. But that variance is likely due to the estimation using that equation.
One of the customer needs is obviously that we need to be able to eject these disposable tips after they've been used. And our NEMA 17 stepper motor has a thrust force of 12.5 kilograms, and that's just a given. And through research online, we were able to find that the force required to eject pipette tips for similar systems is about 5 kilograms. So obviously, because we're able to generate about 250% the force required to eject those tips, we know that our device will be able to eject them.
As far as material selection went, as you saw Jose's portion, we were able to type and refine our design very quickly. So that's why we went with PETG and 3D printing. And then we were able to keep on using that in our final design, as its maximum working temperature is 80 degrees Celsius, which is 10 degrees higher than the customer needs statement. So we won't have any drooping of the material or flexing or bending due to heat. And then as far as using aluminum and stainless steel together for the plunger, they're separated by the O-rings so they don't come into contact with each other, and that's going to prevent galvanic corrosion. And then the plunger assembly does not ever contact any liquid when collecting or dispensing the fluid. And so that's going to prevent the risk of corrosion or bacteria buildup.
Sorry, my mic wouldn't unmute. Okay, so just to make sure that our setup could actually meet the volume precision that we're predicting with calculations, we actually used a real test setup, because obviously there are certain things we couldn't account for in analysis, such as backlash in the lead screw or different varying pressure on the O-rings, stuff we just needed to test in person to actually validate. So we used a test setup, which was essentially a mock gantry motion that would be exactly like inside of the autonomous bioreactor. Then we used an Arduino that was controlled with a computer code we developed with and then controlled through the laptop. So basically, we would input a volume that we wanted to pick up, and then using the code, we could calculate what does that translate in degrees of motion from the stepper motor. So then we could use a water sample to then pick up the amount that we'd commanded. Then we dispensed it back into a graduated cylinder, and then used the precision scale, which had an accuracy of about 0.1 micrograms, which translates to about 0.1 microliters, assuming a constant density for water. So then we could actually look at, well, we commanded this much volume, and that's how much we predicted. Then we could actually measure how much volume actually came out. So we could then characterize the errors within our design. So you go to the next slide, we can actually detail the data we collected. So across our 100 to 1,000 microliter range, we looked at many different volumes in between, and each one we took about 10 trials of data. We took those 10 trials and then characterized the error from the desired amount of volume. And then we used a 95% confidence interval to correct for only 10 samples. And as you can see on the table there, our standard deviation was below 5 microliters for pretty much all volumes that we tested, which is good. That's our plus or minus 5 microliters we need to hit. As you can see by the average error and also the plot below, we were very consistently below the volume we predicted. Part of this is because due to the adhesion of water to the pipette, as you can see in the picture, there's really always going to be a couple little drops that are going to stay back and then be decreasing our volume collected. So in order to account for that, we then modified the code to actually give us a little extra travel direction when expelling the fluid. So that would try to avoid any volume left over inside the pipette. Additionally, we predicted that the seal inside of the O-ring was not actually constant due to surface roughness from the machining of the plunger. As Jose mentioned before, we ended up changing to a precision ground steel rod in order to combat that the seal, because as we were traveling across larger ranges, we're actually seeing a greater average error, as seen by that slight negative slope across the majority of our volume range, just because it was hitting different bumps on the surface roughness, and that kind of varies the amount of liquid we're actually picking up. So you go to the next slide, we can look at our results after applying the differences in the seal Also applying to the code to have extra dispersal and extra pickup based off the average bias error we calculated. So we had a final demonstration of our design where we were just given a random volume and we had to hit it within our bounds. So we were given 500 microliters. We had to hit it within 3 tries. And actually our first try, we got 501.2 microliters, so well within the 5 microliters range. So it just goes to show that we characterized the bias error well and also mitigated some of our difficulties with that extra fluid and the seal of the piston. Additionally, we actually were over the volume requirement we needed. We calculated a maximum volume range that we ever dispersed was 1,107.9 microliters, or we only need to go to 1,000. So we actually get a little bonus on our amount of volume we can actually handle with our pipetter. And additionally, our final code did show that the limit switch was successful at using it to stop if we just commanded it to go all the way up and try to hit through, and also as a 0 point for actually going up, zeroing, and then going down to the volume necessary to take up. And additionally, we also showed that our tip ejector function, sorry, I don't have a video for you right now on the slide deck, but yeah, all good results.
The total cost for our system was $75.47, which is well below our target budget of $100. The largest portions of that were the motor and gantry attachment, which are both static costs given by the customer requirements. The best ways we found that we could probably reduce this cost is number one with our our limit switch. Ours is about $4, but we've been able to find some online that are, less than $2.50. So we could definitely slightly decrease our cost by doing that. Another way we could do that is to try to change our fasteners and the amount that we have. I know most of our fasteners are made of steel, and getting aluminum ones would definitely help in bringing that cost down. So in summary, our design is able to meet almost all the required design requirements. Here's a couple highlights. One of our biggest points is that our volume is way smaller than it needs to be. It's only a third the maximum volume. The only requirement that's really not completely satisfied by our design is the toolless assembly, because we're going to need screwdrivers and stuff like that just to mount our motor and our bottom plate. Thanks for your time, and we'll now take any questions.
Okay. Any questions from our panelists?
So on the cost slide that you had just a couple of slides ago, I don't see anything accounted for assembly cost on here.
Yeah, we don't have assembly cost on here.
Do you have a ballpark of what that would be?
I mean, really the only things that we really only actually manufactured about 2 or 3 parts, so it would be relatively low, but we'll definitely make sure to include that in our final report.
Now, what about what's the estimated assembly time you guys have?
Sub 5 minutes. For sure.
And you're expecting, how many of these are you expecting to make?
I don't actually think we have a number for the number that are going to be produced for the BioFoundry. I don't know if Dr. Nemi can input there.
Yeah, I guess I'm just curious, is this a one-off thing for the lab, or is this a, commercial product that you expect to sell in the hundreds or the thousands or the tens of thousands?
I've got a great answer to that, Tom. Yes.
So I guess my question then related to that would be, how does that impact like some of the 3D printed parts versus other more conventional manufacturing techniques that scale a little better?
Yeah, so if it's actually going to be for the purposes of just producing our prototype for the class, obviously 3D printing worked really well because we had it in the lab. We could just iterate through if we needed to change any dimensions or explore different options. But obviously we're looking at a commercial product, like just the outer casing itself. You're looking at like a print time of 10 to 12 hours if you're doing a 25% infill, which obviously if I'm going to be making hundreds, that's not very like efficient in a time perspective, as well as like the energy you're going to use. And then from a performance perspective, I mean, a 3D printed, due to all the layers, you're going to have some weaknesses in the boundaries of each layer. So if you're looking at a commercial product, it'd definitely be better to use a more conventional manufacturing method to have like a more, to have more longevity and robustness in the design.
Thank you.
Other questions from our panel?
I guess I keep going. Back when we were talking about the force required to eject a syringe or pipette, are we looking at a line of action? I'm looking, maybe the figures are throwing me off a little bit, but on the left side figure, I'm looking at a line of action that's a little bit off center. And on the right hand side, I'm looking at a line of action that looks like it's centered. Is that 12.5 kilograms of which is you know, a weird unit for force? Is that acting like directly concentric with the nozzle every time?
The 12.5 kilograms going downwards.
Yeah.
So, yeah. So what happens is our let's see if I can go pull up a picture. Our drive nut here. This thing, the ejector sleeve, this is actually upside down. So our casing will push down on this top part, the flat part of the ejector sleeve, and the ejector sleeve can slide, and then it will slide and push push that pipette tip off. Because
okay, where is that load being applied on the, I guess on that yellow piece of your snap together?
Yeah, correct. On the yellow piece.
Yeah, where's that load being applied?
Constant. It's just, I just made the load centered because it's uniform throughout the entire thing because it's getting pressed on by this drive nut.
Yeah. Okay, so that load will be what, like sort of in a ring around the hole?
Well, no,
Correct.
it'll apply it on the entire face.
He's speaking on the other end when it's ejecting the pipette.
Oh yeah, it'll just apply.
Yeah, it'll be concentric on the, I guess, that pipette end to push it out.
Yeah, I guess what I'm getting at there is if your load is being applied a little bit off center, you know, you're potentially going to be twisting things, and you know, maybe that causes more force to eject the pipette. Maybe that causes, you know, additional wear in the system, that sort of thing.
Yeah, and I think that's just like a slight error in the PowerPoint. We couldn't get it quite aligned down the center there, but
Okay, yeah.
Yeah, that load is applied through the center. Yeah.
through that center line there.
What do you expect for performance over the lifetime of the system? Like, are there like spots where you expect wear to occur?
The biggest.
Oh, sorry, you can go if you want.
Right. I was gonna say the biggest wear spot is the O-rings. We had to likely the first time we had to replace the O-rings was due to our original plunger. We did not have a chamfer on it when we first inserted it, and we think that is what kind of tore apart our first set of O-rings. But since then we've been using the same set. We just would need to run a lot of trials to see how long they would last before we need to get new ones before they deteriorate in performance. But that would be the quickest failure point.
Excuse me, guys.
What about elsewhere in the system?
Sure. We could also say between the ejector sleeve and that bottom plate would also be, I guess it could be a point of failure, as those prongs are thin. And let's say we're doing constant assembly, disassembly, as well as that translation, as you see in that image there between those prongs there. That could be a point of failure, but we tried to bulk up and strengthen that that portion of the part best we can, just with the direction and printing quality and the density of our actual prints to account for that.
Yeah, another thing I'd like to touch on, since it is 3D printed, everything I could find was that PETG doesn't start to have some plasticity due to heat till about 80 degrees Celsius. However, when we're looking at the bioreactor going up to about 70 degrees Celsius at a max, I am like slightly skeptical about like how much that transition range is for when PETG will start to soften. And since a couple of components are actually held with heat set inserts, for example, the gantry attachment that's actually holding it up. Obviously, anytime that PETG starts to soften, you run the risk of those heat inserts actually ripping out, and then it could fall. So I would put that as also.
That was going to be my next question, so I'm glad you addressed that. Yeah, that's definitely something that's not just a binary on-off, right? The working temperature does not mean that, below that working temperature, you don't have to consider thermal effects. So I'm glad you're thinking along those lines.
Do we have additional questions? Alrighty. If not, then I guess we'll go ahead and wrap things up here. We will reconvene back at 11:30 in the next Pipette time slots. I have updated the Zoom links on the presentation agenda page that we had sent out before. So before you all come back in about 20 minutes, please refresh that page to make sure that you have the most updated link. I am also going to pop the link right here into the chat for everybody, just so that way it is here, just in case I did something wrong. There is the same Zoom chat. We are going to be using the same Zoom meeting for each one of the next 3 presentations, so we don't have to be hopping out every 30 minutes. So we'll be just going through it. I believe it's actually the same Zoom meeting for the rest of the pipettes today. And then we'll have a single Zoom meeting link for the pipettes tomorrow, just to keep things consistent. Also because I was in a mad panicked rush and only created 1 Zoom meeting. Yeah, other than that, great job, guys. Way to be the first victims of the pipette teams. Great job. Congrats. And poke back in later and harass your classmates. So then for all of our sponsors, I'll see you guys in about 20 minutes or so.
Thank you.
Thank you.
Good work, guys.
Thank you.